In this video, I am going to talk about more in detail about analysis of variance. Especially this analysis of variance, we will term it as it's a single objective optimization where we have only one response parameter. Our objective is to optimize only single parameter, not multiple cases. Okay, so here the main thing is we need to know how we have to visualize our analysis, whatever the statistical analysis which we are getting from our statistical tool, or whatever the statistical analysis which we have to perform manually, because nowadays manually it's a very time taking process. So if you know rough idea, some tools are available already. I have discussed about the tools also. So with that particular tools we can able to easily get the statistical analysis parts and all. So in this present video I will try to highlight those things very detailedly. So here I am taking a case study where it's a sustainable manufacturing process. They have machined 17.4 pH stainless steel on turning by using various coolant techniques like cryogenic cooling, minimum quantity lubrication cooling. So cooling fluid they have changed, that's why they are terming it as a sustainable machining process. And this is a reference I have taken. So here you can able to observe we are having four cutting parameters. If you can observe here, we are having four cutting parameters. That is, 1 is cutting speed, 2 is feed rate, 3 is depth of cut, and 4 is the coolant type. 4 cutting parameters we are having here, and these are the levels which we have taken. Cutting speed at this particular level 500, 775 and 1200, feed rate at this level, depth of cut at this level, and 3 cutting coolant type, that is dry machining, where no cutting fluid will be used here, dry machining. Minimum quantity lubrication means very less amount of cutting fluid is going to be used. So this comes under the category of sustainable, this under category of sustainable, because no cutting fluid means it is not harming to the operator, is it or not? So no cutting fluid means it is not causing any harm to the operator. Next, cryogenic is minus 196 degrees liquid nitrogen is going to be sprayed in the cutting zone. So these are the 3 cases. We will have a clean look of this one. Okay, and here these are the things which I have to take it into the Minitab software. Okay, if I open the Minitab software, I have to enter the points like this, like a cutting speed at this particular range, feed rate at this particular range, whatever the ranges they have mentioned, and coolant type I cannot give here alphabets, okay, in the levels type. So I have to give only in the form of numbers. So that's why I am taking a cryogenic coolant as 1, okay, cryogenic coolant as 1, 2 for MQL, and 3 for dry machining. So 3 categories I have taken here. Observe. So this is the screenshot which I have taken from the Minitab. Next. So how we are going to add the experimental details? So we will get a sheet like this after adding the input levels. After the previous screenshot I have shown, no, after taking that one we will get the parts like this, okay, like cutting speed. This is the orthogonal array which it has been formed, orthogonal array. Okay, this part is entire thing is called as an orthogonal array. They have mentioned it here. See, if you can see the cutting speed at 3 levels, second cutting speed at 3 areas, second cutting speed at 3 areas. So you can see it will be unique. Even here also the feed rate, the first level 1, 2, 3. Okay, so this is the speciality of the orthogonal array, where you can able to see in each column equal number of levels has been placed. Okay, so next we will go with the next one. This talks about my output parameters. Okay, this RA and flank wear are my output parameters. After machining the 17.4 pH stainless steel by using sustainable machining, I am going to estimate the surface roughness as well as flank wear. So 2 things I am going to choose it here, RA and flank wear. So RA and flank wear I will copy like this. In this sheet there will be some kind of extension here. Okay, here some extensions will be there. So in these extensions I will add these things here very clearly. Next, so conducting the statistical analysis, So here what we are trying to do is before conducting the statistical analysis, we have to analyze the Taguchi design. So conducting statistical analysis talks about after taking the design, that is orthogonal array we have framed, and we have conducted the experiment, and we have got the outputs we have estimated. Whatever the outputs we required, we have estimated the outputs also in our experimental problem. Now the thing is, we have to analyze these outputs, whatever the outputs we are having. Here in this case we are having surface roughness and flank wear as our outputs. Flank wear, they will try to term it as VB also sometimes, flank wear. So these two are my thing. One is related to the workpiece and one is related to the cutting tool. This is cutting tool. So here how we have to analyze, whether it may be higher the better or whether it may be lower the better. For example, if you take the surface roughness should be, the value should be as low as possible. Lower the value, lower the surface roughness is the best. Similarly the tool wear also. Tool wear, basically how we will try to observe, whenever we are having very less amount of tool wear, the tool life will be high. Tool life will be high. So in the case of productivity, if we talk about the productivity of any machining process, high the tool life will have more amount of productivity. Is it or not? So tool life should be high means what? Tool wear should be low. So here whatever the parameters consider two things are lower the better only. Okay, so lower the better values only. So we will consider the two parameters here as lower the better only. So here after analyzing this Taguchi design, I will get a graph like this. Okay, so in this graph you can able to see, this is the graph which has been plotted for means. So means means in the previous case for RA I am having 1.96, 1.85, like that I am having some values. So the values means they will try to plot it in the form of a graph like this. This is for surface roughness only. This plot is for surface roughness only. Again for flank wear there will be some other graph I am not showing here. I am not representing those graphs here. Okay, and how we are getting these things we will see it in the next slide. So if you try to observe, these are our area output, and here see this peak point. So this peak point how we will get? So by adding the levels, whatever the corresponding levels, 500 at which level, 1.85, 1.96 and 2.33 divided by 3, we will get the average as 2.046. This is the 2 and somewhere we are getting the maximum mean value. So this is the mean value which we can able to see it. And similarly the low value also, this particular point, the corner point, this will be somewhere in between 1.4 to 1.5. So that also we can able to estimate by using this particular formula, this range. So here this range we are talking about this one, 1, 2, 3. 1.21 plus 1.65 plus 1.56 divided by 3 will get 1.473. Somewhere between 1.4 and 1.5 will get the mean. So now based upon this one, all our values will be lied in between this range only, in between 2.046 less than or equal to mean less than or equal to 1.473. So here only our values are going to be like. So this is the way how we are estimating the mean. So mean in most of the cases, mean should be as low as possible, because that also again depends upon the parameter. Here we, in our case, we are considering for surface roughness and flank wear, we will consider as low as possible. Okay, I hope you got this particular point. Next, so what are the mean effects plots and how we have drawn? I have given the a general overview. Now we will go to the S by N ratios. So as I have discussed in the previous video, S by N is signal to noise ratio. As Taguchi has framed this one, we have to reduce the noise. Whatever the noise it may be. So this noise should be close to 0. Whatever the value, suppose it is a positive value, it should be close to 0. Suppose it is a negative value, it should be close to 0. Negative or positive, it should be close to this 0 level. Okay, so now here if I try to see the graph, totally I have got contradiction from this particular graph to this particular graph. But here you can able to observe one point they have done. signal to noise ratio smaller the better. See, this is the graph for surface roughness, that is RA. For RA I have to consider the smaller the better value. So that's why the signal to noise ratio I have applied the formula for smaller to better. So that I have got a graph like this. Here if you try to observe, this is minus 6.5 and minus 3 is here. What I have said is the signal to noise ratio value, it should be very close to 0. So now I will consider this parameter as a major parameter. This parameter as a major parameter. Similarly for feed rate also, which one? This particular point. Similarly for depth of cut, this one is very high, this one is medium and this one is low. Similarly for coolant type, this is medium, this is low and this is high. At last we can able to term it as A3, B1, C3, D1. A3 means what? Coolant type at third level. This one, coolant type, this one is A, this one is B, this one is C and this one is D. So coolant type at third level, feed rate at first level, depth of cut at third level, and this one is coolant type is at first level, and these will give me optimal parametric setting. So this is talking about S by N ratios, related to S by N ratios. Okay, so remaining things will be changed depending upon their requirement again. Okay, next. So this response table ratios, how we have to calculate? So here we have got some values. No, here we have got, for example, say this one somewhere from 3.09. This value will be somewhere like 6.479, like that. Some value will be there, some random value. So how we are getting that values, that is important here. So here this is the output which is generating from the Minitab Taguchi analysis, RA, that is surface roughness versus cutting speed, feed, depth of cut and coolant type, and we are getting the signal to noise ratios and mean graphs like this. Now let me explain this one first, then I will go how we will get the individual terms here. See here the delta talks about maximum minus minimum. Here what is maximum? Minus 6.179 is the maximum value. Maximum value is minus 3.289 is the maximum value, minus minimum value is minus 6.179. So minus of minus it will become plus, so you will get 2.889. so this is our delta value which we have got here. Similarly we will calculate for these things also. Here the maximum value will be this, minimum value will be this. Here the maximum value will be this, minimum value will be this. Here the maximum value will be this, minimum value will be this, so that you will get these values. Okay, automatically maximum minus minimum. What we have to observe is we have to observe maximum minus minimum values. Now among this all these delta values, which is the highest one? 2.89 is the highest one, followed by 1.806, followed by 1.540, followed by 1.342. So now I will give the ranking here. By this ranking, what we have to conclude is cutting speed is the most influential factor, followed by feed rate, followed by coolant type, followed by DOC, depth of cut. So this is the things which we have to conclude for the surface roughness. Remaining things and all, flank wear and all, we did not done right now. Okay, so this is the conclusion which we are drawing. Now how we will get this particular value, that is important for us. Okay, so let me take this one. This is the RA which we are having with us. Okay, for this particular RA, how we have to estimate this particular value means RA at which levels we are having. For this is now we are talking about the first level and cutting speed. For the first level cutting speed, it is at first experiment, second experiment, third experiment. What are the corresponding values of the RA here? 1.85, 1.96 and 2.3 33. So these are the corresponding values at first level cutting speed. So now what we have to do? So based upon this one, we have to substitute in this formula. Smaller the better, we are having the formula. So how I will do is, I will substitute minus 10 into log of 1 divided by n. So how many number of trial experiments I have to done? So here I have taken 3 experiments into, so this log should be for both, summation of 1.85 square, like this, 1.85 square, 1.96 square, 2.33 square. These values I have to take, and I will get 0 minus 6.719. So that value I have highlighted here. Similarly, if I have to go for the second one, that is for the feed rate at level 1. Now you see here, now I will erase all these things. Now my objective is to calculate this one, feed rate at level 1. So feed rate at level 1, where and all it is there? This 0.96, fourth experiment, and seventh experiment, these values are there. So what I will do is minus 10 into log of 1 divided by 3 multiplied by 0.096 whole square plus sorry, not 0.096, at 0.96 we are having 1.85 square. Next, regarding to this one, we are having 1.61 square plus 1.21 square regarding to this one, whatever the value. So these values we have to do it, and we will get the value as minus 3.172. So like that we have to calculate the remaining all things. But why I am saying this one is, Taguchi will directly give us the correct values only, but we have to know how we are generating the theory behind this one. Okay, so that's the reason I am going to explain like this. So smaller the better is going to have an explanation for this one. Similarly, for larger the better, there will be some other formula like minus 10 into log of 1 divided by n summation of 1 by r square. So this will be formula for larger the better. So formulas will be going on changing like this. So smaller the better, larger the better, and nominal the best. So depending upon this one, we have to calculate. I hope that you got a clear answer how we are getting these values. Similarly, for the means, I have showed now in the previous slide I have shown how we are getting 2.47 and 1.47. Similarly, you try to estimate the middle also. Okay, so middle also simple case. Here it is very simple. Now I will try to calculate for cutting speed. Okay, so for cutting speed, what are the values? 1.61 plus 1.26 plus 1.85 divided by 3. So you will get definitely 1.573. So like this. So like this I will get this value. So this is very simple case here. So this is the procedure we are calculating for the mean. Okay, let me go to the next one. So main effect plots of the flank wear. So flank wear also we will have a similar case. This is the point for means. Here cutting speed at A, feed rate at B, depth of cut at C, and coolant type as the D parameter. Similarly, S by N ratios also we are getting like this. What I have said is we have to consider the signal to noise ratio close to 0. 0 indicates that there is no noise. Okay, if it is plus means there is positive noise, means maybe high noise. Maybe minus means very low noise, that is internally. Like that we can think and we can assume this one. Our objective is to be very close to 0. So here how we are going to calculate cutting speed at first level, and feed rate also at first level, and depth of cut at second, that is middle level, and coolant type again at first level. So these are the things like what we will get. We will get A1, B1, C2, D1. Sometimes researchers will be mentioned in their paper like this: A1, B1, C2 and D2 are the optimal parameters. Then it is difficult for us to analyze. So A1 indicates that cutting speed at first level, B1 indicates that cutting speed at first level, C2 indicates that depth of cut at second level, D1 indicates that coolant type at first level. So like this we have to analyze. So this is a simple case. Again this is the S by N ratios for the flank wear also. So now in the previous case we are talking about the RA, now we are talking about the flank wear. So flank wear also we are getting the smaller the better. The same formula again we will use here, and this formula how we are trying to decode it. So 33 first value, 53.6 and 91.83. If you substitute these things we will get 34.74. Okay, similarly the mean values also, the corresponding values if you try, for example in the case of this one, 33 plus 53.6 plus 91.83 divided by 3, you will get a 59.80. so this is the value we are getting here, that is for the means, and the remaining thing and all same here. How we are getting the delta, how we are getting this rank, is everything is related with respect to what we have discussed for the surface roughness. Okay, you can remember those things. Next, how to visualize the estimation, like ANOVA estimation, influential factors. Here most important thing is ANOVA table will give like this. Here what is the degrees of freedom? So degrees of freedom I have said that level means number of experiments minus 1. Here we are having 9 experiments, minus 1 is 8 experiments will get. So 8 degrees of freedom. So the residual error is 0. So now we can able to omit this line. Here we did not got the F value and P value also. So omit this particular line. Okay, no, not necessary for us right now. And this is the sum squares SS. Okay, as you can remember we have discussed in some of the SS, some of the squares for treatments in ANOVA video. Adjacent squares and adjacent mean squares. So from here this is our most important thing, how we have to estimate which is the influential factor. So this influential factor is talking about like this. So cutting speed, if I take cutting speed means this 14.159, the cutting speed corresponding value, okay, divided by, and here the cutting speed levels, how we are getting the degrees of freedom as 2 means 3 levels are having 3 minus 1 is 2 degrees of freedom. We will take like this, divided by 26.1611, so that we will get 54.12. So this is the way we have to estimate the percentage. Similarly for feed rate we are getting this much, similarly for depth of cut this divided by this, and similarly for coolant type this divided by this, we will get this one. So among these values, if you try to observe, among these values which is the highest value? Cutting speed is the highest value first, followed by feed rate, next followed by coolant type, followed by depth of cut. So this is what the conclusion I will give here. Cutting speed is the most influential, followed by feed rate, followed by coolant type, followed by depth of cut. So like these conclusions we have to give it in the paper, in our research papers after conducting our experiment. Okay, next one is empirical modeling. See here, empirical modeling, why this modeling is used to do for forecasting or for prediction of various parameters, machining parameters, or to know the behavior of your experiment. So there are many things are there. Okay, so now the empirical model here is this one. This is of linear model. Okay, so here if you can see we are having a constant here. Okay, a constant value will be there, followed by cutting speed, followed by feed rate, followed by depth of cut, followed by coolant type. All our 4 parameters will be there, and R is called coefficient of determination. So this coefficient of determination, it should be lie in between 0 to 1. Okay, definitely it should be lie in between 0 to 1, but this value should be more than 0.95. If it is more than 0.95, then only the fit is best. Here for the case of RA, this fit is okay only, but it is not that much best. Whereas in the case of flank wear, 93.2 means 0.93, it is as close as 9.95. So the fit is almost all best only. some papers we will get 0.96, 0.99. So this indicates that the coefficient of determination is going to be takes place as close as possible, as nearer as possible, like that we have to assume. Okay, so this is the empirical model, or we will try to term it as mathematical model, which we have extracted from the set of experiments which we are having with us. So this is also will be there under the category of modeling and optimization. Some of the papers, if you try to observe, modeling and optimization means what? They are going to develop some kind of a model for our easy visualization of the process. Okay, next one, here the normal probability curve we can see here. So this is some typical graph which we can see. So this red line is talking about the probability line. Okay, this will be like similarly y is equal to mx plus c, some straight slope will be there, no, similar kind it will be there. Whatever these values should be very close to this particular line, and the difference from here to here is called as an error. As I have discussed in earlier videos also, this is called as an error. Okay, so this I have discussed more detail in ANOVA analysis. This probability curve talks about how much close our value is, Next, confirmation results. So confirmation results means what? Now I am going to predict something. Okay, so based upon that predict, I will try to conduct some experiment. Okay, I will, after conducting some experiment, and I have to check that whether that part is correct or not. Now in the previous window, I have got this equation. Now this equation I will try to substitute here. See, this is my equation. I will substitute these values here. Now what I will substitute is like this: 1.67 into 0.00769 into V is, for example, I will take with the first level, that is cutting speed at first level. Next, 3.76 is the constant which I have got, and 0.096 is the feed rate at first level, and 0.458 is the depth of cut constant, and 0.2 is the depth of cut which I have got. Next, 1.553 into coolant type is 1. I will substitute here, so that I will get 1.708. But when I have conducted the experiment, I have got 1.85. But when I have conducted this one, I have got the value as 1.708. The difference between these two things is called as a residual. Okay, this one. So how fit our model is? Suppose I am developing a mathematical model depending upon a set of 9 experiments here. So from these 9 experiments, whether the model is adequacy or not, how I have to check? So by using the fit option, and this fit option, if the error is less than 10%, okay, error means maximum value minus minimum value divided by maximum into 100. If you go into, you can get that error percentage. So if the error is less than 10%, then we can say our fit is best. Otherwise, there is some deviation in the statistical part. This deviation can be identified. So this is the way how we have to estimate. Similarly, you substitute for the next one also. I will write it here. RA for second experiment, 1.67 minus 0.00769 multiplied by 500. Next, plus 3.76 into, what is the second level? 0.413143. Next, minus 0.458, this 458 multiplied by D is, depth of cut is 0.4 multiplied by 0.4. Next, plus 0.1533 multiplied by CTV is coolant type is 2. If you substitute this one, we will get 1.9465. 1.9465, this value will get. But our value is for RA is 1.96. It is very close. Maybe 0.13 is the difference. So this is the way we have to confirm our result. And the next one is, we are going to predict our things. So prediction of results, how we are going to predict this? So here the prediction Basically the prediction setting is going to be takes place depending upon the optimal parameter level. So this one, cutting speed at 1200, feed rate at 0.96. Cutting speed at 1200 means I can say this is at level 3 A3. Let me go back fast. This is for flank pair, no, not for flank pair. We need for this one. What is this one? A3 B1 C3 D1. A3 B1 C3 D1. A3 B1 C3 D1. See here, A3 B1 C3 D1. So A3 in the S-band analysis we have got the optimum level. A3 is at 1200, B1 is at 0.96, C3 is at 0.6 depth of cut, and D1 is at coolant type 1. And here if you try to fit, we are getting the fit as 0.96. Means 0.96 is the RA value, okay, and this RA is at 95% confidence interval, 95% confidence level, and 95% probability interval, okay. So these intervals are more important. I have a separate video on this same confidence interval, okay, so that we can understand this one. And this is the graph which it is showing, and 1200 is the optimum level, 0.16 and 0.6, and coolant level at 3. If you take high, we will get this value, or we can go for minimum, means we will get 0.896 at this level. This is the minimum, okay. So 1200, 0.96, 0.6 and thing. If you need high surface roughness, very high value, go this one. If you need low surface roughness, go to this value. So like that this table is going to be predict, like, means the ranges. This is not if you do with this particular thing we will get the highest. This is a range. This is a range of the input parameters which we have selected, and this is the optimum value which we have got from the case. And if you try to compare this one with the previous values what we have got, see here you cannot able to see we did not got 0.986, 0.986 we did not got it, okay. We did not, means that particular researcher did not got it. Now this researcher will conduct an experiment with 1200 cutting speed and feed rate at 0.96 and depth of cut at 0.6 and coolant type at cryogenic, and he will conduct that experiment. After conducting that experiment, whether he is getting this particular same surface roughness or he can estimate. So that is the uniqueness of this optimization. So from the given set of the results, if we are not able to get the best one, so there is a chance to predict which is the furthermore better one. Maybe I am doing this experiment is not available. If you see 1200 is there, 0.096 is there, 0.6 is there, but coolant type at MQL is there, but coolant type cryogenic is giving the best thing. That is coolant type, if you are having 1, it is giving the better result. Here it is 1.21. If you conduct the experiment, you may get 0.96 also, or very closer, or you may get 0.7 also. That kind of challenging is going to be given by this kind of Taguchi. Okay, this experimental layout will try to give. Now totally if I conduct the 10 experiments, the 10th experiment will be this one. So depending upon this experiment, I can able to optimize my part, and this is for single objective only. That's why my only objective is one level. I am trying to go for single objective, and multi-objective I can discuss in the case of desirability function analysis as Bayes relation analysis. You can see the multi-objective how we are doing. Okay, so this is the way we have to conduct the single optimization, and we have to analyze our statistical analysis. Thank you.